Hi guys, welcome back to Think Tank Online Learning. Okay, so in this tutorial we're going to talk about continuity and limits of complex numbers. Okay, so given that c is a complex number and we want to show that the limit as z approaches infinity of 2z plus I over z plus 1 is equal to 2. Okay, so there are about two methods of working out this problem. The first one is by using Lhospital's rule, then the second one is using substitution. Okay, so I'm going to start by using Lhospital's rule here. So this is method number one. Okay, and what we're going to do, we're going to differentiate the numerator. Okay, so we're not going to use quotient rule, but we're just going to define the numerator separately and differentiate the denominator separately. Okay, and after that we're going to the limit is going to be numerator over denominator. Okay, so the limit of the numerator over the limit of the denominator, and that is going to give us 2. Okay, then the second method, okay, before going to the second method, Lhospital's rule is only applied when you don't have z conjugate here. Okay, so this is z and this is z. Okay, so now I'm going to score the numerator. Okay, let me just say numerator is g of z. Okay, so it's 2z plus I. Okay, and if we differentiate that, z prime is going to be 2. Okay, and now we're going to the denominator. I'm going to call the denominator h of z, so it's going to be z plus 1. Okay, and now if we differentiate e to the respect to z, we're going to get 1, and the limit of this function is going to be limit as z approaches infinity is going to be 2 over 1, so the limit is 2. Okay, then the second method we're going to use substitution. Okay, so we can't just substitute infinity here, because if substitute infinity we're going to get infinity plus 1, and that is going to infinity, and here we're going to get infinity again, so infinity of infinity is undefined. So what we're going to do, I'm going to divide each and every term by z on the numerator. Okay, so I'm going to say 2z over z plus I over z divided by z over z plus 1 over z. Okay, nothing has changed. The value of the equation is still the same, but only just the appearance. Okay, and now we can cancel z. Okay, and after doing that, I'm going to substitute my infinity. So I'm going to say limit as z approaches infinity, okay, of the function 2 plus I over z over 1 plus 1 over z. And what I'm going to get is that I'm going to get 2 plus I over infinity over 1 plus 1 over infinity. Okay, and you should know that any number divided by infinity is 0. Okay, you can just try 1 divided by 1 million. Okay, you're going to get an answer that is approaching 0. So here I'm going to get 2 plus 0 over 1 plus 0. Okay, so as you can see, 2 plus 0 is 2, 1 over 1 plus 0, so the answer is going to be equal to 2. Okay, and the first method, when I given a function like that, okay, you can just, the power of z is 1 and the power of z is 1, so you can just compare the coefficients. So the coefficient of z is 1 and the coefficient of z is 1. So the coefficient of z is 2 and the coefficient of z is 1, so the limit is just 2 over 1. Okay, so to check if the function is continuous, what we're going to do, first we have to determine if the function is defined at this point, okay, at xy equals to 0. And as you can see, the function is defined when it's equal to 0, the function is 0. Then the next thing we're going to do, want to determine if the limit exists at this point. Okay, so now what we're going to do, we're going to check whether if the limits exist. Okay, unfortunately we're not going to use Lhospital's rule, because this is z and this is not z squared but z conjugate, so unfortunately you can't use a hospital's row, and if we use substitution, we're going to get 0. Okay, so want to think of another different approach. And when I give a problem like this, I think using polar coordinates is one of the best. Okay, but you should just remember, you should keep in mind that y is no longer r sine theta, but it's now I r sine theta. So I'm going to say x is equals to r cos theta, y equals to I r sine theta. Okay, so z is a complex number, so I'm going to say z is equal to x plus iy. So that means z conjugate is equal to x minus iy. Okay, so z in polar coordinates, z is equal to r cos theta plus I sine theta. So z conjugate is equal to r cos theta minus I r sine theta. Okay, so it's I r sine theta. Okay, so I'm going to use a pen, because if I use a med marker I'll run out of space. Okay, so what we're going to do, I'm going to say limit is r approaches 0, okay, of 2. Instead of writing z conjugate squared, I'm going to say r cos theta minus I r sine theta squared over r cos theta plus I r sine theta. Okay, and what I'm going to do, I want to rationalize. I'm going to multiply the denominator and the numerator by the conjugate of z. Okay, because I want to obtain a real number, and my goal is to get rid of r in the denominator so that I can substitute r equals to 0. But if I substitute r equals to 0, the function will be undefined. So I'm going to multiply both numerator and denominator by the conjugate. Okay, so it's r cos theta, and the conjugate is negative I r sine theta. Okay, so it's r cos theta minus I r sine theta. Okay, and now I'm going to say limit as r approaches 0. Okay, so as you can see, this is same as this, so I can just say 2 r cos theta minus I r sine theta cubed over. Okay, so if we multiply a complex number by its conjugate, we're going to get a real number. So here I'm going to get r squared cos squared theta, and I'm going to square I r sine theta. And if you square that, you're going to get positive I. Okay, it's now positive. If eliminated I, positive r squared sine theta. Okay, so if I could say I r sine theta times I r times negative I r sine theta, I was going to get negative I squared r squared sine squared theta. Okay, so negative 1 times I squared is equal to positive 1. Okay, so now I want to expand this, and I'm going to use Pascal triangle. Okay, so these are the coefficients of Pascal triangle. It's 1, 2, 1, 1, 3, 3, 1. Okay, you can use binomial expansion. Okay, so limit is r approaches 0 of 2. Okay, so first I'm going to get r cubed cos cubed theta plus r squared cos squared theta I r sine theta. Okay, plus r cos theta I r sine theta squared, okay, plus I r sine theta cubed. Okay, and I'm going to put my coefficients. Here it's 1, here it's 3, 3, 1. Okay, and this I'm going to divide this by, okay, let me just factorize here, r squared, so it's going to be cos squared theta plus r squared. Okay, so now sine squared theta, as you can see, this is equal to 1. Okay, and as you can see, we have r cubed here, and r times r, it's also r cubed, then r times r squared, it's r cubed, then r to the power 3 is r cubed. So I'm going to factor out r cubed, so it's going to be 2r cubed. Okay, then here I have cos cubed theta plus 3 cos squared theta sine theta. Okay, and I squared is -1, negative 3 cos theta sine squared theta minus I sine cubed theta, okay, all divided by r squared. And now r squared into r cubed, I'm going to get r, and now I can substitute, so it was lim is r approaches 0. And now if I replace r with 0, I'm going to get this whole, this expression is going to be 0, so I'm going to get 2 times 0, and that is equal to 0. So as you can see, the limit at this point is equal to 0, and the function is defined at the origin. And now we want to check our last condition so that we can determine whether the function is continuous or not. Our first condition, the function is defined at this point, it's when z equals to 0. Okay, we've shown that the function is defined, so it is defined at z equals to 0. Okay, then the second, we've shown that the limits exist at this point. Okay, at the point xy equals to 0. Okay, so the limit is xy approaches 0, 0 exists. Okay, then third, the limit of f xy as xy approaches 0, 0 is equal to f x0 y0. And as you can see here on the third condition, 0 is equal to 0. So I can say that if this function is continuous. Thank you for watching. I hope for your support in form of comments, likes, and subscribing.